Okay, so now let's practice Snell's law and the lens maker's equation. Really, we're practicing lens maker's equation. And we're going to look at these two lenses. One is a decent thin lens. We have large radii of, oops, so we want to be able to draw here. We have large radii of curvature and relatively thin lens. It's only 2 millimeters thick. Here we have a thick lens, and we have a very small radius of curvature, which means we're going to have relatively large refraction angles, which means our small angle approximation is not going to work. What we're going to do is we're going to do each of these using Lensmaker's equation, and then we're going to go to the code and we're going to look at and see how good of an approximation it is. All right, so let's do this one first. On the left, the easy one, not the easy one, the good one. So the first interface is facing this way, and the second one is facing to the left. So we're going to have a positive and a negative radius of curvature. So let's write our equation. 1 over f is equal to n minus 1, 1 over r1 minus 1 over r2. Plug in the stuff we know. We know that 1 over f is equal to 1.512 minus 1.0 times 1 over, now R1 is the leftmost interface, and it is 180 millimeters, but it is facing to the right, so it is positive. Then we're going to subtract 1 over 300 millimeters, which is the other interface, R2, but it's facing to the left, so it is actually a negative 300 millimeters. We plug that into our calculator, turn the crank, and we get that our focal length of this lens is equal to 219 millimeters. Now let's look at the lens here on the right. We see that it has a first radius. We're just going to go straight to this stage right here. 1 over f is equal to 1.512 minus 1.0 times 1 over, now its first radius is facing to the right, so it is a positive 35 millimeters. Then its second radius is also facing to the right, so it's minus 1 over positive 200 millimeters. Now with this one, we turn the crank on this, and we get that our focal length is equal to 82.2 millimeters. So that's great. That's easy, right? Relatively straightforward. Let's see how well it works in practice. One of the things that I hope that you guys take from your undergraduate education is that every model has flaws, right? There's no such thing as a perfect model for any physical phenomenon. There's always a trade-off between cost, effort, and accuracy, right? So Lensmaker's equation is low cost, right? You can do this in 2 lines with a calculator. But as we'll see, it's relatively low accuracy as well. So I'm going to now share a different screen. Hold on, I have to stop. Zoom is not the best. All right, let's share this one. Great, that is hard to read, so I'm going to see if I can shrink this. I can't. Let me stop sharing this, shrink my window, and then start sharing it again so you guys can see it a little bit better. All right, so share screen, Jupyter Lab. That's better. You guys can actually read that now. Okay. So what we're going to do is here is the problem we were looking at before, right? I just cut and pasted it from the PDF. You'll notice, again, this is just Markdown. So if I wanted to make a title, I just do it this way with a single hashtag. And then adding a image is really easy. I just use this notation, this syntax here. Put in the file name, and then I just run that cell, and it displays the image for me. So I'm not going to go through it in this quite as much detail as I did in the last one, but we are going to import NumPy and import PyLab. Remember, NumPy is a numerical library for Python that allows you to do fast matrix algebra. PyLab is a plotting library. And then we're going to import our ray tracing code, which, because we are not in the same folder, we have to use this notation here, which is from ray tracing code, which is the folder right here that our ray tracing code that you downloaded from Blackboard is in. We're going to import this module and stock lens list. And then we're going to load our lens library. Cool. So we got to add 2 lenses to our library because these lenses are not in it. And the way we're going to do that is through this here. And I'm going to post this this notebook to Blackboard so you guys can play around with it if you want to. So yeah, we're going to add this lens. The first lens is the thin lens here on the left. It has a left radius of curvature of 180 millimeters. And remember, this ray tracing code actually uses not radius of curvature, but curvature. And it's the curvature is just the inverse of the radius of curvature. So everywhere I just do 1 over a length, just because it's easier to talk about radius of curvature, because that's what all the websites use when they talk about their lenses that they're selling, right? So we have 1 over 180 because 180 is our radius of curvature here. And then our our right hand interface is facing in the negative direction. So it is a negative 300 millimeters. And so we put in negative 300 millimeters here. And our thickness of our lens is 2 millimeters. Then we're going to do our second lens the same way. Thickness is 10 millimeters. The first radius of curvature is 35 millimeters. The second one is 200. You notice they're both positive, and they're both positive because they're both facing in the positive direction to the right. Vector facing the center of each of these curves faces to the right, so they're both positive. Yeah, that's awesome, and that's done. So we execute this, and then we set up our initial ray. We're actually going to set our wavelength to be 740 nanometers because that's going to match our index of refraction. If we go to refractiveindex.info and look at BK7 glass, we've chosen BK7 glass for our lens, and the reason we know that is because it shows up twice. It shows up as N2 on the first interface and N1 on the second interface. So it's the inside material. And I just looked up whatever wavelength it was that matched our index refraction. So this is 740 nanometers. This is at the bare edge of what you could see. This would look like a really deep red. You'd barely be able to see it, but you could probably see it. Okay, then we set everything else up and run the simulation. So we're going to first try let me see here 1 second. We're gonna first try our lens 1. We're gonna put 50 millimeters before it and then 350 millimeters after it, just so it's big enough that we can see the start of our ray and where it hits the optical axis here. Our orientation is 0 because we don't want to flip it because we put it into our library in the orientation that we want it. Remember, if we put a 1 there, that flips the lens around. Then we create our interface list, put the interface list and the init ray list into our ray tracing function, and we get our ray results, and then we can plot our ray results using this. And then I just added a horizontal line in order to mimic the optical axis so we can figure out where that intersection is by eye and kind of estimate our focal length. So if we run this, we get a focal length of, well, we can't really see, but it looks like somewhere around 200, something like that, a little bit more than 200. So if we zoom in, which means we just replot it using the same function we did before, replot our horizontal line, but change the limits on our x-axis from 200 to change the limits to 260 to 270, and our y-axis we change the limits from 0.2 to negative 0.2, so 0.2 to negative 0.2, 260 to 270, we can actually see that our intersection occurs right around 264.5. So if we subtract the distance from the rightmost part of our lens, which is 52 millimeters from our origin, we can get that our focal length is about 212 millimeters. We can be much more accurate though, because all the information we need to calculate the actual intersection point of our ray is available to us. So if we look at our ray results, we can choose the first ray locations, which is 0, and then we pick the second to last interface. So if we look back at our simulation, where our ray ends is the last interface, because it's like our camera. Our second to last interface is the last interface on our lens. So we put a -2 in here, and that gives us our location. We do the same thing with our direction, but directions are stored in 1 for the middle place here. And with that direction, we get a direction cosine. We can actually find the angle by taking the inverse cosine, arc cosine of that direction 2, and then take the height of that ray and divide it by the tangent of that angle. Cool. And then we can be a little bit more accurate here because, and actually, let's zoom in and I'll show you what I mean here. So let's make this 48, and then we're going to zoom in on our lens. Make this one 55, and top is going to be 7, and the bottom is going to be 0. So if we do that, we should zoom in right on our lens, and we can see that this lens curves up and to the left here on the right-hand side, and where the ray leaves is actually a little bit to the left of 52 millimeters. So we need to calculate that distance. Then to do that, we find the location of the exit of the ray along the x-axis, which is here. This is, again, the first ray. We only have one ray, so it's just 0. Locations, the second to last interface, which is the last interface of the lens, and then the X or Z location. Because remember, in actuality, the way the simulation works, the Z axis is the optical axis. So it's the second or the third, but Python starts at 0, so it's we put a 2 there. Okay, so we subtract that from 52, which gives us a delta x. We subtract that from our f2, and we find out that our focal length, if we run this, it'll print it out for us. Our apparent focal length is 213.7 72 nanometers. Now let me just make sure I ran everything. I did not run the init ray list, so let's run that again. Note that if you want to run things, there's a shortcut. You can just do Shift Enter. So you do Shift Enter, and it makes it kind of quick to be able to run stuff. So that actually changing our wavelength, and this is good to know. Remember, we talked about chromatic aberration in one of the lectures. Changing our wavelength changed the index of refraction, and it changed our focal length. So here we got our apparent focal length is 219.8 millimeters, which, if we are comparing that to our calculations, is only slightly longer than what we calculated before, which is 219 millimeters. So for this lens, the lens maker's equation is quite a good approximation. Let's go through and redo this now, but let's redo it for lens 2. So we just put in lens 2 because that's what we called it when we added it to our lens library. So we could just reuse that there. Yeah, so we actually don't need to run any of this stuff up here because it's already in memory. All we just have to rerun is this cell. So we're gonna do Shift Enter and run it. And we can already tell that this lens has a much shorter focal length because look how much earlier this ray hits the optical axis than before. Before it was out here, and now it's down here. And this lens is much thicker. We can actually see this lens on this plot. If we zoom in on the lens itself, oh gosh, the right-hand side isn't even in our field of view. So we have to actually change our right-hand limits. Let's make it 63 millimeters because we know our lens is 10 millimeters thick. So we're gonna have to be more than 10 millimeters from the left-hand start, which is 50. And now we can see that we can actually see the ray deviate and go down within the lens, which means we know right from the start that our thin lens approximation is not good. Okay, so great. Let's zoom out a little bit. We know that the intersection is going to be right around 230 to 130 to 150. So we can find that intersection with the optical axis by doing 130 on the left, 150 on the right. And let's make the top 1 and the bottom -1. If we do that, oh, there we found our intersection of our ray with the optical axis. And we can zoom in if we want, but we can, with reasonable accuracy, call that 132.5. So if we subtract 60 from that, we get that our focal length is 72.5. But let's, again, do this much more accurately. And to do it more accurately, we've already stored our ray results to the same variable as before. So we just have to rerun these cells, and this cell will now calculate our new apparent focal length. So our new apparent focal length is 88.47 millimeters. And if we compare that to what we calculated before, we calculated 82.2 millimeters. So we are off by a significant amount. And the reason we're off is that our small angle approximation doesn't work anymore. It doesn't work very well. Where was that? Well, let's go back to looking at the lens itself. What did we do? We did 48 millimeters. So our left-hand bound of our plot is just before the lens, and our right-hand bound of our plot we want to be just after. So let's make it 62. And we want our limits to be, the top we want to be above the ray that we used, which was 7 millimeters, and the bottom to be 0, because we want it to be the optical axis. Yeah, so we can actually see the deviation of the ray within the lens due to this strong curvature on the left-hand side. The last thing I want to talk about is how we need to change this real quick. I want to be able to make this a little bit more flexible. One of the things you want to do whenever you're writing programs is, as much as possible, do not hard code in numbers. So here I hard coded in 5 millimeters as the height of the ray. But let's say we want to change the height of the ray, we would have to change it here in our initial ray list, and then come back down here and change it here as well if we're trying to figure out how that changes the focal length. So I'm going to actually code in so that every time I change initial init ray list, it will change this distance here too. So we're going to call initial ray list. And to call that first distance, we can look at the structure here. It's the first thing here, first list. Sorry, it's the first item, which is the first ray, right? And then it's the first item in that list, and then it's the first number in that list. So we have 3 indexes we're going to have to use, and it's the first one in all of them. So we just put a bracket and a 0. This is how you access indices in Python. 0, 0. Okay, so let's just run this real quick just to make sure this works. We got before 88.47. If we rerun it with that new code, we still get 88.47. So we didn't introduce any bugs by changing that. So let's go back up here now and see what happens when we change the height of our array. So let's make our array basically near our optical axis. So let's make that 0, 01, let's say. And let's rerun everything. See, our ray now basically overlaps with our optical axis. If we keep running this, again, it's very hard to see our ray here, but if we actually changed our zoom so that our top was 0.03, so very close to the optical axis, now we can see it. And now we can see that the deviation within the lens is actually quite small. So let's run it and see and calculate it, and we still get 89.18 as our focal length. So what I'd like to press upon you here is that the height of the ray, or the distance from the ray from the optical axis, affects the focal length of that ray. It's still pretty close to what we had before. Before it was 88.7, here it's 89.1, but still, that's some aberration. And this is just not a very good lens, that's not well corrected for aberrations, which is why we can see it so plainly. Cool. So, lessons to learn from this. Lensmaker's equation works pretty well when we're working with thin lenses like this lens on the left, which is 2 millimeters thick. All of our radii of curvature are large. This one's nearly 200 millimeters. This one's 300 millimeters. It does not work well when we have it does not work well when we have small radii of curvature. So we have 35 millimeters here, which is a small radius of curvature. And so it ends up causing some errors as a result of that. Great.